Okay, so what I want to do here in hopefully about 30 minutes is to summarize the topics in Chapter 10, and really these come in two varieties. The first is goodness of fit tests, in which you're trying to determine whether the data itself meets a expected frequency of equal or a specific proportioning of unequal expected frequencies. And I think the easiest way to do this is to say that you are asked for goodness of fit tests typically when you are asked whether the numbers match an expected pattern, and typically this involves a column which has numbers in it, but also a column which are descriptive, which are just nominal in value. I think the easiest way to do this is to simply go through a couple of examples. In one example, I'm actually going to do it the old-fashioned way by calculating the value of the test statistic, which reminds me to say that all of the tests in Chapter 10 are tests in which they're all right-tailed. So anytime the test statistic is higher than a critical value, you would reject the null hypothesis. So the two things that you have to learn to do with all these tests is to write the null and alternative hypothesis and understand how to calculate the test statistic. You can still use the p-value method of making a decision, but you do need to consider what the actual statement of the null is or the alternative is, because there is no chart to tell you how to describe your conclusion. You simply have to say what must be true depending upon your decision. So what happens is that the null hypothesis in a goodness of fit is typically described as either all the proportions are the same or they are unequal in an expected pattern. So let's just do a example here. So here you have someone who's drilled a hole in a six-sided die and filled it with a lead weight, which means they're trying to make a funny die that will selectively roll some number more than other numbers. But anyway, they tried that and they rolled it then 200 times. And here are the observed frequencies. So the possible outcomes still for rolling a die are the numbers 1, 2, 3, 4, 5, or 6. And what they got was 27 ones, 31 twos, 42 threes, 40 fours, 28 fives, and 32 sixes. Now, I know some of you have trouble parsing that out. The word respectively is what is important here, and it says that the outcomes are listed exactly the same as the counts, okay, so in the same order. And it asks you to use a 0.05 significance level test to test the claim that the outcomes are not equally likely. Now, whenever you actually have this statement of the claim that they're not equally likely, what you're actually going to run is an equal expected frequency test. And if you reject the null hypothesis, then you've proven this claim that the outcomes are not equally likely. So the null hypothesis here is that the outcomes on rolling the die are equally likely. So we would put the proportion of ones equals the proportion of twos equal the proportion of threes equal the proportion of fours equal the proportion of fives equal the proportion of sixes. Okay? And then the alternative would be at least one of these proportions is not as stated. Now it's important to get that null and alternative correct. And for equal expected frequencies, that's what you'd have. Now, to do this by hand, you also have to consider degrees of freedom, because your calculated critical value is a chi-square critical value, which is a distribution that we haven't really talked about. I'm not going to talk about it very much here except to explain to you how to read this table, which is table 6. But the degrees of freedom is the number of different possible outcomes, that's K, minus 1. Okay, so there's 6 possible outcomes, minus 1 is 5. So the degrees of freedom are 5. And we have an alpha significance level of 0.05. So if I go to the chi-square table, which is table 6, looks like this. I want to be on the line for 5 degrees of freedom. And my alpha level is 0.05. So you can see that my critical value is 11.071. Okay. So from the table, we have that critical value. Since all the tests in this chapter, both goodness of fit and the other independence test, are all like right-tailed tests, we reject the null hypothesis whenever the test statistic is greater than the critical value. So our challenge is to calculate the value of the test statistic. And again, I'm doing this by hand, and then I'm going to show you how you could have done it using StatCrunch. And all of these handouts are in your course content in Unit 5. Okay, so this is not magic. The value of the test statistic is equal to the sum of observed minus expected squared divided by expected. Okay, so, and incidentally, this formula is, of course, in your key formulas handout or pullout. Okay, the easiest way to do this is to actually put it in a table like this. So here are all my possible outcomes, and here are my observations of my possible outcomes. Okay, I took that directly from the description of the problem. My expected value here is 33.33 because my expected value is the number of times I repeat the experiment divided by the number of outcomes. And honestly, this just makes sense. If I roll a die 200 times and it's a fair die, okay, there are 6 possible outcomes, the numbers 1, 2, 3, 4, 5, or 6, then I expect to get approximately 33 of each of the possible outcomes. Now, the expected number is allowed to be a decimal number. It doesn't have to be a whole number, okay? So I've just carried it to 2 decimal places here. Okay, so I've listed that expected value because I should get that for every single one of the outcomes as long as the die is fair. Okay, so then what I've done is I'm trying to get to this thing, so I see I need observed number minus expected number. So I'm taking this 27 and subtracting 33.33, and that gives me negative 6.33. And then I square that. Now, when you square a negative number, you get a positive number because negative times negative is positive. Many people make this mistake on their calculator. Okay, so warning, this is a mistake. Okay, what they do is say negative 6.33, or whoops, negative 6.33, and then they hit the square button, and it shows them a negative value, but that's because you're not squaring the negative 6.33 here. Your calculator is an educated 2-year-old, okay? When you have an exponent, it only applies to the thing directly to its left. The thing that is to the left of this 2 is the number 6.33. If you want it to be negative 6.33, you have to put the negative 6.33 in a parentheses. Now you're going to get the right answer. So none of these numbers here in this column are ever negative. because they're all squares. And negatives times negatives are positive, as are positive times positive. Okay. So then after I do that, I take the O minus E squared number and I divide it by the expected. So what I'm doing is I'm taking the 40.0689 and I'm dividing by the 33.33. And that's how I got this number here. Then I do that for every single one of the outcomes. Okay? So again, I take the 31 and subtract the 33.33. That gives me negative 2.33. I square it and I get 5.4289. Then I divide by the 33.33 and I get this number. When I have done that for all 6 possible outcomes, I add this column up, and that's the test statistic. Because remember, this directive right here is sum all of those, right? That is Greek letter, capital Greek letter chi, and it means to sum, okay? So then we make this decision by saying, since that test statistic is less than the critical value, we fail to reject the null hypothesis. Now, we failed to reject equally likely outcomes, which means that there's not enough evidence to support the claim that the distribution is not equally likely. And sometimes we say that the distribution here is not uniform. Equally likely and uniform are the same type of distribution. Okay, so you could quite rightly say, well, that's a lot of work. Is there an easier way to do this? And yes, there absolutely is an easier way to do it. So what I'm going to do is this same problem using StatCrunch. And there is a handout for that right here, okay? That's in your course content. Okay, so I'm going to change my share to my screen. And I'm going to go to StatCrunch. Now, what I'm going to do is I'm going to put the observed values. Okay, so observed values. And when you're running a test of equally likely outcomes, you don't have to put in the expected values. It can do that for you. So you go now to Stat, down to Goodness of Fit. You want to do a chi-square test, and the observed are in the column that we labeled O, and then you have to check that I expect all cells in equal proportion. That's telling us you ran an equal expected frequency test, and then you hit compute. And so this is what you get, if I can get this to move over. Sorry, my picture's in the way here. Okay. All right. So you can see that they've already listed for us that 33.333, et cetera, is going to be the expected value. This thing here, the chi-square, is the test statistic. And then this is the p-value. Now, this is the reason, honestly, that I wanted to also show you how to do it on StatCrunch. Because if you go with StatCrunch from the get-go, you do not actually have to know the critical value, all right? Because you can do this with a p-value test. So in this case, you would be saying that the p-value of 0.3201 is less than or greater than, you have to ask yourself that question, the alpha value, which was 0.05, okay? Clearly this p-value is greater than that alpha value, and that means that you fail to reject the null hypothesis, okay? So I'm going to change the screen again and just show you the way I wrote it down on my presenter window, right? I compare the p-value with the alpha value, so that was 0.3201 to 0.0500. This number is bigger than that number. That means I failed to reject the null hypothesis. And again, I'm failing to reject that the outcomes are equally likely. So my conclusion is that there's not enough evidence to support the distribution is not equally likely. Now, I know that's confusing, so you really need to think about it before you write your conclusion. There is no magic chart that will tell you the wording to use in doing this. The other kind of test that you can run in this first section is what we call an unequal expected frequency. And that's like this problem that I'm posing here. So in this case, it's about the World Series. So this is the count for the World Series. This is actually last year. So it didn't include last year's World Series. And it does omit 2 World Series that went to 8 games, and I can't even remember why. But anyway, this is the proportions that would be expected if the teams, assuming that the teams have equal abilities, using an 0.5 significance level, test the claim that the observed frequencies agree with the theoretical proportions expected. Now, I'm not going to do the math here to support these expected proportions, but they are correct, okay? So 2/16 of the time, 1/8 of the time, we expect that the World Series would be won in a sweep, right? In only 4 games. 25% of the time, we expect it to take 5 games. 5/16 of the time, we expect it to take 6 games. And 5/16 of the time, we expect it to take all 7 possible games. So the null hypothesis must reflect those expected proportions. So in this case, it would be null hypothesis is proportion that ends in 4 games equals 2/16. Proportion that ends in 5 games equals 4/16, comma, proportion in 6 games equals 5/16, comma, proportion in 7 games equals 5/16. You have to explicitly state the expected proportions in the null hypothesis. And then the alternative hypothesis is, again, like in the other one, at least one of these proportions is not as stated. Okay? Now, on this handout, I have gone on to write down how you would do it by hand, but I'm not going to do that. I'm going to go directly to StatCrunch here and use the p-value method. So I'm going to change the share to my screen. Okay, and I'm going to get rid of this one, clear the column. Okay, now in this column, I will put in the observed values. Okay, so that's 18, 20, 22, and 37. And then I will put in a column of expected values. Now, honestly, I think you might be able to put in the fraction, but I'm not sure. So I think what I'm going to do is try that, just because I know that's what you all would tend to do. It'll probably give me an error, but if it does, I'll go back, and don't think that it allows me to do not do the division myself. Oops. Okay, but I'm going to go up here and I'm going to go back to stat, goodness of fit, chi-square. The observed are still in the column labeled observed. The expected are in the other one. Okay, see, it's not even allowing me to choose that because it already knows there's an error. So 2/16 is 1/8, so that is 0.125. And it may not even allow me to do this. Because it may expect me to calculate the expected number based upon the same idea as when you try to get X from a proportions issue. If I have to do that, I'll come back to it. Okay, that's 0.25. And this is point. Let's see if it'll allow that now. Okay. Right, so now I've got them as decimal numbers, and let's see if it'll do that. Okay. All right, so that's good because it would have been more confusing for you if they hadn't allowed it. So now notice, the only thing I've changed here is I've changed the expected values from a fraction into a decimal number, right? So that shouldn't be a challenge. Here again is your test statistic right here. And then here's your p-value. And so to do this, we will again compare the p-value with the alpha value. So the p-value is 0.0616 and the alpha value is 0.0500. Okay, so now let me go back to my presenter window. Okay, this number is bigger than that number. And again, that means that we would fail to reject the null hypothesis. But in addition, notice that where it has the expected values on StatCrunch, it's exactly the same as these numbers here, okay? So it has done the test correctly. And now you have to write the conclusion sentence. So again, we failed to reject this idea, right? And so we would have to state there's not enough evidence to reject the claim that the observed frequencies agree with the theoretical proportions or frequencies. Okay? So honestly, I do not expect you guys to do these by hand. I expect you to use StatCrunch and do them using the p-value method. But if I ask you for a critical value, you should be able to use Table 6 to get it. And you should be able to use the results from StatCrunch to tell me what the test statistic is, right? So down here, this was the value of the test statistic. And if you had looked up the critical value for this thing, it would have been 7.815. Again, this value is to the left of this value, and all of these are right-tailed tests. So it would again indicate that we failed to reject the null hypothesis. I really suggest that you print out this handout to reference while you're doing your open book test and your lab in Chapter 10. Okay, so that's one section. The next section of this chapter is about tests of independence. And tests of independence involve looking at variables and their relationships presented in contingency tables. And I am not even going to do one of these by hand, even though on the lab you are requested to do it by hand. There's 2 or 3 examples that you are given in the textbook, and you can just follow those examples to do the lab problems. For example, I'm going to look in your textbook. It goes thoroughly through a problem about how gender is related to what type of ice cream you like to eat. Okay, and I'm actually going to take the time to put this contingency table down here. So the 2 variables are gender and favorite ice cream. And the question we're asking is your gender a factor in what kind of ice cream you prefer or how you like to eat your ice cream? And they've got a whole bunch of them: cups or cones or sundaes or sandwiches or other. Okay, so the table looks like what I'm drawing here. And so there were 504 men who preferred to have their ice cream in a cup, 474 women. There were 287 men that preferred a cone to 401 women. There were 182 that preferred a sundae that were men, and 158 that preferred a sundae that were women. There were 43 men that preferred a sandwich, 45 women preferred a sandwich, 53 men said others, and 50 women said other. Okay, now if you are doing this by hand, you need to follow the instructions on page 537 in the text. It shows you how to get the expected values. Okay, and then it goes on to show you how to use those expected values to perform the test of independence. I'm going to go straight to StatDisk with this because I know that's really how you're going to do it. But first you need to understand what the null and alternative hypotheses are here. The null hypothesis, if you wrote it generically, would be that the row subject and the column subjects are independent of one another. Okay? So in this case, I mean, you can't use the generic form. You have to write it out specifically. So you would have to say that gender, which is the row subject, okay, and favorite ice cream, I guess, style, are independent. And then the alternative hypothesis is that your gender and your favorite ice cream style are related or dependent. I prefer the word related. Okay? So those are the two hypothesis statements. And again, your decision will be either to reject the null hypothesis or to fail to reject it. So let's look at this particular one in StatCrunch. And what I'm going to do is I'm going to put this contingency table basically the way you see it in StatCrunch. Okay, so that's going to take me a second. I'm going to show you how to do that. So I've got to change my share to the screen. Okay, and in fact, let me see if I can just open a new window. Okay, so the rows are male and female. Then the first column is like use a cup to get your ice cream, and then the next one is cone, and then the next one is sundae, and then the next one is sandwich, and then the next one is other. Okay. And then here is the table numbers themselves: 504, 474, 287, 401, 182, 158, 43, 45, 53, 50. Okay, so that looks almost exactly like what you saw when you were looking at the contingency table on page 537 of your text. So to do this, though, this is the important thing. And yes, there is a StatCrunch handout on how to run an independence test, okay, with a contingency table. That handout is in the course content of Unit 5. Okay, so I'm going to go to Stat, and I'm going to go down to Tables, then across and down to Contingency, and then with Summary. Okay, so I need to select all the columns. So Cup, and then I need to hold down the Control button so I can add the others. There should be one other. Where's the, oops, didn't mean to make that smaller. Don't even know how I did it. Hope you can still see it. Okay, then when it's where it says row label, you need to choose bar 1 because that's where male and female are listed under it. Okay, then all you have to do is hit compute. If I knew how to make this bigger, I would. I don't know what I've done. Okay. So you should be able to see on here that where it says value, that's the value of my test statistic. But the important part here is where it says p-value. And so the p-value for this is 0.0005. I compare that to my alpha value of 0.0500. Okay, and I'm going to go back to my other screen, back to the presenter window. This is the p-value that was given by my results in StatCrunch. This is the alpha value. This p-value is clearly much smaller than the alpha value. And when the p-value is less than the alpha value, you reject the null hypothesis. So going back to the null hypothesis, we are rejecting this idea, which means we have evidence to support that gender and ice cream style are related. Full stop. If you reject the null hypothesis, you're essentially supporting the alternative hypothesis. But remember that when you write a conclusion statement, I expect you to reference the row and column subjects. Just as when you write the null and alternative, I expect you to reference the specific row subject and column subjects in your problem. If you do it generically, like if for the conclusion you simply say the rows and columns are related, I'll take off points. I'm just going to tell you straight up, you have to reference back to the problem. Okay? That's essentially all there is in Chapter 10. So I'm going to call it a day, and hopefully you're going to watch this before you try to do Lab Chapter 10 or do the open book test. Please remember that the open book test is a hard deadline. None of them will be accepted after that Monday, the 22nd. I believe that's the date. I'm not really sure. So it's whatever the Monday is in finals week or the last week of classes. And I believe that's the 22nd. Okay.